In this video we're going to cover stereoisomerism. So for the sort of molecules that we're going to be encountering this semester, it's really where carbon has 4 different groups. So that will tell us if a molecule is chiral. So here we've got these images, we've got the carbon in the center and then 4 different groups around that carbon. So they're just indicated there by the different colors. So you can see with the ones on the left and the right, the green and the red, that they are coming out towards us, and then the yellow and the white groups are then going back behind the molecule. So this carbon has a tetrahedral shape, and these 2 images here are mirror images of each other, and because we've got these 4 different groups on that carbon, then these are non-superimposable. So a bit like our left hand and our right hand, they are mirror images of one another, but they are non-superimposable. So you can't overlay your right hand and your left hand and have everything lining up. The same here with these molecules. So we can't pick up the molecule on the right, rotate it so that it's the same orientation as the molecule on the left. So this would be then a chiral carbon because it has these 4 different groups attached to it. They don't have to be 4 different elements, so it could be methyl and ethyl. They would be counted as 2 different groups. So rather than writing these ball and stick diagrams all the time, there's a few different ways that we can represent this. We can do it with dashes and wedges here. So these wedges are coming out of the plane of the paper towards us, and these dashes are going back behind the plane of the paper. So the way I remember this is the ones left and right are like 2 arms coming out to hug you. So that's the dashes and wedges there. We can also draw them as Fisher projections, which is just using these lines, but this is representing the same as this dashes and wedges here. So the ones left and right are coming out of the paper towards us. The ones vertically there are going back behind the plane of the paper. When we're comparing these Fisher projections, there's a few rules in what we can do in terms of rotating the structures. So we can't rotate them 90 degrees, but we can rotate them 180 degrees. So if we have these 3 molecules here, and I was to say 2 of them are identical and 1 is not, and then you need to work out which is the pair of identical molecules. So if we look at them, if we look at the first 2 structures there, you can see the hydroxyl group is on the left in both of those, but you can see that the other groups have changed. So we've got the carboxylic acid at the top, it's underneath in the second one, methyl group underneath, up the top in the second one. And so very difficult to compare them directly. And then if we were to compare, say, the first and the third one, so carboxylic acids group line up, methyl groups line up, but then the hydroxyl groups are on opposite sides, the hydrogens are on opposite sides. So we know that the first and the third one are mirror images of each other, and they are non-superimposable. So they're not the pair that are the same. So what we want to do with this second molecule is to rotate that around so that the carboxylic acid and the methyl group line up with either the ones on the left and the right, and then we can compare which side the hydroxyl group is on. So what we can do with this molecule here is to rotate everything 180 degrees. So this is our second molecule. We're going to rotate it 180 degrees, so the methyl group will go down to the bottom, the carboxylic acid group will go up the top, the hydrogen will go around to the left, and then the hydroxyl group will go around to the right. So we end up with this structure here. So now that we have that, very easy to compare and say that this structure is the same as the one on the right up the top. So compounds 2 and 3 there were the same structures. So we can rotate that whole molecule 180, but we can't rotate it 90 degrees. So an example of that is in your practice end of semester exam paper. So you were given this structure here, and you're asked to classify that as either a D or L sugar, and whether it's an aldotetrose or a ketotetrose. And so for these Fisher projections, what we want to have is either the aldehyde or the ketone as high up to the top of the molecule as we can. So if we look at this one here, you can see that the aldehyde group is towards the bottom. So when you're answering this, you would actually have to redraw this and rotate that structure. So if we rotate everything there 180 degrees, then that CHO group, that aldehyde group, will go up to the top. CH2OH will go down to the bottom. The hydroxyl groups there will flip around to the right side as we rotate at 180 degrees, and the same with the hydrogens, they will go around to the left side. So this would be then the image that you would have to look at to determine whether or not it's D or L and aldotetrose or ketotetrose. So the first thing we can probably do is work out it's an aldotetrose. So aldo is aldehyde. So we've got this aldehyde group there. So keto is from the ketone. That's not a ketone functional group. So then we want to work out whether it's a D or L sugar. So we already know it's either A or B, or it could be none of the above, but it is tetrose, so 1, 2, 3, 4 carbons. So it is a tetrose. It's an aldotetrose. It must either be the D or L. So we're looking for the configuration of the hydroxyl group on the carbon furthest away from the aldehyde group. So carbon 2 is chiral, carbon 3 is chiral, but carbon 4 is not. It's got 2 hydrogens attached to it. For it to be chiral, it needs to have 4 different groups attached to it. So at carbon 3, the hydroxyl group is on the right, which means it's a D sugar. So this is going to be A, it's a D sugar, an aldotetrose. So if you hadn't rotated it, you'd probably look at that hydroxyl group and think it's on the left, so it's an L sugar, but you must rotate that one to have the aldehyde group up the top. So option A is the correct answer there. This is from the short answer questions of the practice exam. So in this one here, we're asked to draw both the mirror image isomers that exist for the molecule below, first of all as tetrahedral, so wedge dash representation. So we've got CH3, C, Br, OH, CH2, CH3. So what that is trying to represent there is that we've got, so every carbon is going to have 4 bonds. We've got a CH3, so that carbon has got 3 hydrogens attached to it. It's going to have then a bond to this carbon. So this carbon must have 4 bonds. So 1 to the first carbon, 1 to the bromine, 1 to the hydroxyl group, so to the oxygen of that hydroxyl group, and then the 4th bond will be through to this carbon here. And then, so there's our 4 groups attached to this carbon. We've got a methyl group, a bromine, a hydroxyl group, and an ethyl group. So if we want to draw that as wedge dash representations, so we can have the way there's probably a few different ways you could draw it. The way I would draw it, we're going to have the wedges left and right there, and we're going to have the dashes going up and down. And for the first image, it doesn't matter where you put those 4 groups. So I'll just put them in this order here. So we've got methyl group up the top, hydroxyl group on the right, ethyl group down below, and the bromine on the left. So that would be one of the isomers. So to draw the other one, then I've drawn the mirror image of that. So the hydroxyl groups there are on the inside there of that drawing, and the bromines are on the outside, and then we don't change the other 2 around. So these 2 here are mirror images. So they are non-superimposable because we have that chiral carbon in the center. And then very easy then to turn those into Fischer projections. So instead of now drawing the dashes and the wedges, we just need to draw the single lines for these. So these are representing the same molecules as the dash wedge representations on the left. So there's our Fischer projections. So the term to describe these are enantiomers. So these are non-superimposable mirror images. So they have the opposite configuration at every chiral carbon, and there's only one chiral carbon for this molecule. So enantiomers. So enantiomers, as I've just said there, so non-superimposable mirror images. So one enantiomer will rotate light clockwise, so it's given the plus symbol. Its mirror image will rotate light to the same amount, but in the opposite direction. So if the plus one rotates at 20 degrees clockwise, the negative one will rotate at 20 degrees counterclockwise. So they will rotate light the same amount, but just in opposite directions. as we increase the number of chiral carbons in a molecule, then there are more stereoisomers possible. So this is given to us by the formula 2 to the power of n, where n is the number of chiral carbons in a molecule. So in this structure I've drawn here, we've got, so carbon 2 would be chiral. It's got 4 different groups attached to it, so hydrogen, methyl group, bromine, and then this group below. And then carbon 3 would be chiral as well, so it has 4 different groups attached to it. So 2 to the power of 2 would be 4, so there are 4 possible stereoisomers for this. So I've drawn all 4 here in this diagram, and then there are different relationships within this. So where we have, so the bromine, the chlorine, right, if we swap the configuration of both of those, so they're left, then these two here are mirror images, so they have the opposite configuration at every chiral carbon. We could have the bromine right and the chlorine left, and its mirror image would have bromine left and chlorine right. So again, that relationship there, they have the opposite configuration at every chiral carbon, so they are enantiomers. If we start back with this first one, so right, and we swap the configuration at one but not both, so bromine right but chlorine left, so these two here, these are not mirror images. They have the opposite configuration at least one but not all chiral carbons. So these are diastereomers. So the red lines here are showing the relationship there that are diastereomers, so they have the opposite configuration at one but not both in this instance. And then the blue lines here, the diagonals, are showing enantiomers. So these have the opposite configuration at both of the chiral carbons. With Meso compounds, so these have chiral carbons in them, but they also have a plane of symmetry about the molecule. So if we look at these two structures here, so carbon 2 is chiral, has 4 different groups around it, and carbon 3 is chiral, and so then the mirror image of that molecule on the left is the one on the right. However, if we look at that in more detail, so you can see then this plane of symmetry about the molecule. So everything on the top half of that is then reflected in the bottom half. So the top half is a mirror image of the bottom half. So the result of that is if we were to take, so this structure, the top left one there, rotate everything 180 degrees, then methyl group would go down the bottom, methyl group would go up the top, so we've still got methyl groups at either end. The hydroxyl groups on the right, we rotate them around, we've got the hydroxyl groups on the left, which is then this structure here. So these two here, they are mirror images of each other, but they are now superimposable. So they are, they have this, because of this plane of symmetry about them, these two molecules are now identical, and so this is called a Meso compound. So it does not rotate plane polarized light. So the relevance of this in terms of biological molecules is where we have two chiral molecules interacting. So we might have a drug, for example. So we've got a carbon in there with 4 different groups around it, so that's a chiral molecule, and that can interact with a receptor site on a protein. So where one enantiomer of this is going to line up perfectly with the receptor site, so you can see there that square fitting in the square box, the triangle there in the triangle, circle in the circle, and so that might be a very good interaction between that drug molecule and the protein. The mirror image of that drug molecule, though, has the opposite configuration, and so for that, where the square might line up, but the other two groups do not. And so the chemistry is going to be quite different for that. So there might be then quite an adverse reaction. And an example of that is with thalidomide. And so thalidomide is a chiral drug molecule, and there was quite devastating effects of that. So with the wrong enantiomer having then not matching up with the protein molecule, and then that resulted in quite devastating birth defects on many babies.